Understand what do we mean when we say motion is relative or relative motion. Relative term we all know. Relative means when we find out something in comparison with something else, in relation to something else. So for example, we can understand this by taking an example. Let's say there is a body A which travels a certain distance. Let's say it travels a distance of 10 meters to reach from the initial position to the final position. It travels a distance of 10 meters. And there was another body which was next to it, let's call it body B, which travels only a distance of 5 meters and then it stops. Right? So A travels a distance of 10 meters before it stops, and B travels a distance of 5 meters before it stops. Now as B stands here at its final position and looks at A, according to B, how much distance has A moved with respect to B or as seen by B? Do we see that this distance will come out to be nothing but 5 meters? So we can say that in relation to B, A has travelled a distance of only 5 meters. Or in physics we call it relative to B, A has moved only 5 meters. Right? Understand that one important aspect of finding out the motion of A in relation to B or relative to B is that B being the observer, while it looks at the motion of A, it does not consider its own motion. It does not take into consideration the aspect that it has also covered a certain distance. It only sees how much distance has A moved as seen by him. That means when B observes, when B is the observer always considers himself or itself at rest. The observer considers itself to be not moving. It could have a motion of its own, but it will not consider that while observing another body. So this is one important aspect of studying relative motion. Relative motion means we are trying to study the motion of a body with respect to an observer, which could be at rest or it could be moving, but that observer always considers himself or itself at rest. And with that condition, it studies the motion of the other body. So if you can understand this basic aspect of relative motion, things will become quite simple for you. You will be able to do questions related to relative motion quite easily. So we say here that the displacement of A as seen by B or with respect to B or relative to B is 5 meters, only 5 meters. Why? Because A travelled a distance of 10 meters, actual distance was 10 meters, but then B has also travelled 5 meters. So if we just subtract this 5 from 10, we will get 5 meters as the displacement of A relative to B. Right? Now mathematically, if we want to express this, how do we do that? We know that the displacement of A is 10 meters and displacement of B has been 5 meters. Now according to what we have discussed just now, do you understand that the relative distance of A with respect to B, this is how we write this, will be the displacement of A minus the displacement of B? It is 10 meters, the actual distance travelled by A, minus, subtracted from that, the distance travelled by B. This will give us the displacement of A as seen by B or as with respect to B or relative to B. Okay, and hence this particular formula then becomes an important formula when we talk about relative motion, the motion of one body as seen by the other. How do we find out the relative? What we have got here is the relative displacement actually. So the displacement of A as seen by B will be the displacement of A minus the displacement of B. Okay, and what we have discussed just now is for a displacement. We will see this later on, that this will be valid for other aspects of motion like velocity and acceleration as well. Okay, so let's say for example, if we have a car A which is running with a speed of 10 meters per second towards right, and there is another car B which is running with a speed of 5 meters per second towards right on the same road, just they are moving one next to the other. If we want to find out the velocity of A as seen by B or with respect to B, by definition it will be velocity of A minus velocity of B, from the same argument that we have made in displacement above. Okay, so as B sees A, B will see that A is moving only with a speed of 10 minus 5, that is 5 meters per second. We have observed this in day-to-day aspects as well. When we travel on road, we know that there are vehicles which are moving along with us on the same side as in which we are moving. We feel as if all those vehicles are running slowly in comparison to, let us say, the vehicles that are moving on the other side of the road. They are the ones which are coming from the front and crossing us, moving in the other side. We generally feel those vehicles to be moving faster in comparison to the vehicles that are moving in the same direction in which we are moving. That happens because when we do VA minus VB, for the vehicles that are moving along with us, their velocity gets decreased, no? With respect to the velocity with which we are moving as observers, right? So here also understand this important aspect, that when B observes A, B will consider himself to be at rest. The car B will consider itself to be at rest and then will measure the speed of A. So it will come out to be 10 minus 5. Okay. So this is a basic aspect of relative motion. Here we have discussed relative displacement, and here we have considered relative velocity. Okay, and the same thing goes for relative acceleration as well. Relative acceleration, if we have to talk about, we say that if there is a body A which is moving with an acceleration of, let's say, 2 meters per second squared, and there's another body B which is moving in the same direction with an acceleration of 1 meter per second squared. In that case, the acceleration of body A as observed by body B or relative to body B, it will be acceleration of A minus acceleration of B. So it will be 2 minus 1 meter per second squared. Okay. Now the next thing is, what we have observed here just now is only a scalar aspect of relative motion. Why? Because we have taken all the directions one way. We have considered both the displacements in one single direction, the velocities in one single direction, and the acceleration also in one single direction. We can expand this arena to 2 dimensions also, where we will study relative motion in 2 dimensions in a plane, and the basics will remain exactly the same. They will not change here. So that is what we shall discuss next, relative motion in a plane. So in 2D, let us first discuss a body A which is moving towards right, let us say, and it has, let's say, traveled a distance of 4 meters. There is a car, let us say, which is moving on the road, travels a distance of 4 meters, and there is another car B which was initially adjacent to it, and it moves a downward distance of 3 meters. Okay, so after some time the car A will be over here, A will reach here, and B will reach here. Now how do you see this? How will the car B see the position of the car A with respect to itself as seen by B? How has the car A moved? Do we see that as seen by B, car A is somewhere here now? It has moved like this. Initially both car A and B were at the same position. They started off from almost the same position. But after some time, when the car A reaches here and B reaches here, as seen by B, the car A has reached over here now. It has not just moved towards right, it has also moved up as seen by B. Understand, this is important. We are considering here B as the observer. That means B is looking at A all the time as to how A is moving, and while B is looking at A, B is considering itself at rest. So B is not taking into consideration its own motion. For B, it is only A that is moving and B is not moving. Okay. So when B looks at A now, the displacement of A has not been 4 meters. Do you understand? this length that B sees A to have travelled will be actually 5 meters. This comes from the Pythagoras theorem. These two directions are perpendicular to each other, 4 meter and 3 meter. So this particular length will come out to be square root of 3 squared plus 4 squared using the Pythagoras theorem, which will give us 5, isn't it? So according to B, or as seen by B, A has actually travelled a distance of 5 meters. And not just that, according to B, A has not moved towards right. A has actually moved in this direction, which if we consider the rightward direction as the eastward direction and the upward direction as the northward direction, according to B, A has moved in the northeast direction. So as seen by B, A has not just moved a different distance, it has also moved in a different direction, right? So in that sense, relative motion gives us an entirely new picture of how a body moves. As seen by different observers, we say that if different observers observe a single body, according to all of them, the motion of that body would be different depending upon how those observers themselves are moving, right? So in that sense, relative motion is a little tricky. You have to be really good with working with vectors. So if you haven't been thorough with vectors yet, I would suggest all of you that you go back and revise your vectors portion. I have taken all the videos on vectors, so if you want, you can just go through them once. Be thorough with addition and subtraction of vectors. That will help you here in studying the aspects of relative motion. So in this particular case now, if we want to find out the displacement of A as seen by B, and this time when I write this expression, I will write it to the vector form, because I know now that displacement of A and B are not in the same direction. So I cannot consider them like scalars. I can't just add or subtract them. I have to take care of their directions, right? So by definition, once again, as we have studied in 1D, in one dimension, displacement of A with respect to B, or as seen by B, should be by definition displacement of A minus displacement of B. And this time we are supposed to do a vector subtraction, right? So we have to take care of directions. How do we do vector subtraction? If we just recall, in vectors, if we have to subtract two vectors, we can rewrite it as displacement of A plus minus displacement of B. This is how we can rewrite it in mathematics, right? And what this means in vectors is that we are trying to add vector SA, the displacement of A, we are trying to add it with the negative of the displacement of vector B, or the displacement of the body B, right? Now how do we show this in figure? Let us draw this figure once again. We are saying that the displacement of A is 4 meters towards right, like this. Let me draw it a little to the side so that we have space. This is the displacement of the body A, we call it SA. This is towards right, isn't it? And this is the displacement of body B, downwards, SB. What are we supposed to do? We are supposed to get minus of SB, negative of the displacement of B, which we understand from the information of vectors will be this vector. Just equal and opposite to vector SB will be the vector minus SB, negative of displacement of vector B. And now we are supposed to add these two. How do we add these two vectors? We know how to add two vectors using the triangular law of vector addition. We just need to join the tail of vector SA with the head of the vector SB. This is SAB, the displacement of A as seen by B. See that this vector that we are getting here through the figure is coming out to be same as the vector that we have drawn over here, right? In fact, we know that if the magnitude of this vector is 4 meters and the magnitude of this vector is 3 meters, then the magnitude of this vector will come out to be 5 meters using the Pythagoras theorem. We also let's say we want to find out the angle that this displacement vector of A with respect to B makes with the horizontal, makes with the displacement SA. Can we from this figure write tan phi is equal to the opposite side, which is this length 3 meters, by the base length, which is 4 meters. So it will be 3 by 4. Tan phi is 3 by 4. So from there we can find out the angle also. We know that This angle phi will take a value of 37 degrees in this particular case. Tan phi is equal to 3 by 4 for phi is equal to 37 degrees. You can check this from the trigonometric tables. So, see here what we are saying. Once again, the displacement of A as seen by B is not 4 meters, it is actually 5 meters, and this displacement is such that it makes an angle of 37 degrees with the eastward direction. This is how B sees A to be moving, right? Actually A is moving towards the right, but when B sees it, the motion of A changes. Why? Because B itself was moving. So, this is the importance of relative motion, how the motion of a body changes just when you change the observer, the way the observer is moving when it is observing the body, that changes the whole motion of the body. In fact, this is a very basic aspect related with motion. We say that all motion is relative. Anything that we observe to be moving or at rest, it's just with respect to us, with respect to the observer who's observing the bodies are at rest or in motion, or they are in motion in a certain way. If you change the observer's motion, then corresponding to that observer, the way the body is moving, that will also change, right? Similar example we can take in velocity also. In 2 dimension, when we try to find out the relative velocity, which actually is a very important concept in the chapter kinematics, relative velocity, we shall be using the same basics, no change in the basics at all. It's just that we have to work with vectors this time, so we have to be very clear with the vector addition, the aspects of vector addition and subtraction. So, just to take another example, let's say there are 2 cars A and B which crossed each other at a crossing. Car A was moving at 10 meters per second towards right, and car B was moving at, let's say, 5 meters per second downwards. Just taking same directions for the sake of convenience for now. We can change our example later on. And the question is, we are supposed to find out the velocity of A as seen by B. As a passenger sitting in the car B observes the passenger, or the car A, the passenger sitting in the car B observes the motion of the car A, how does it find the car A to be moving? We use the same definition. We say that the relative velocity of A with respect to B by definition will be velocity of A minus the velocity of B, the vector difference between the two velocities, which we can do, right, by using the vector diagrams for addition and subtraction of quantities. This time let us try doing the same question using the rectangular components of vectors. Okay, let's see if that makes the working easy for us. So, what we do here is, we consider the Cartesian system, x axis here, y axis here. In terms of x and y axis, do we see that velocity of car A can be written as 10 meters per second I cap, because the car A is moving along the x axis, positive x axis. So, using vectors, this is how we can write this. Velocity of car B, on the other hand, which is moving along the negative y axis, see that positive y axis is upward. So, it will be minus 5 meters per second j cap. And now what we are supposed to do is, we are supposed to find out velocity of A with respect to B, which is by definition velocity of A minus velocity of B. When we substitute the values here, velocity of A is 10 meters per second I cap, minus velocity of B is minus 5 meters per second j cap. See what we are getting? We are getting 10 meters per second I cap plus 5 meters per second j cap as the velocity vector for A with respect to B. This is the vector that we are getting corresponding to the relative velocity of A with respect to B. Let us see what we are getting this in figure. In the figure, 10 meters per second I cap will be a vector like this, 10 meter per second I cap, and 5 meter per second j cap will be a vector like this, 5 meter per second j cap. So, the sum of these two components will be a vector which will point like this, isn't it? So, this is our resultant vector, velocity AB, velocity vector AB, which will have a magnitude which we can easily find out. Do we understand how to find out the magnitude of a vector which is given in the rectangular component form? It will be square root of 10 squared plus 5 squared, isn't it? Right? So, which we can take 5 out here, which will come out as 5, and within the square root we will have 2 squared, that is 4 plus 1, so 5 root 5, right. So, the magnitude of this vector will be 5 root 5, whereas what will be the direction that it will make here? If we call this angle as theta, can we say tan theta will be equal to the opposite by the base, which will be 5 by 10 or 1 by 2. So, from here you can write theta is equal to tan inverse of 1 by 2, right. So, once again we can find out our relative velocity vector just in the vector form, or if you want the magnitude, this is what we can do, or we can also find out the angle. Everything we can find out just if we are thorough with the basics of vector addition and subtraction, because this is the basic definition. If you know how to use this definition correctly, how to solve it in vectors correctly, then it's quite simple. And then you need a little bit of visualization. See here that as A moves rightwards and B moves downwards, as B reaches here after some time, as seen by B, A has reached here. So, as seen by B, A has actually been moving like this in this direction. So, this is the direction that we have obtained here, isn't it? So, relative motion, or in particular relative velocity, is a topic where you need to be thorough with vectors as well as a little bit of visualization. If you can visualization situations correctly, there is no point you will make a mistake. You will always be able to get your answers correct. Okay. Maybe a particular special case I will take up here. In 1D itself, let us say there is a body A which is moving with 10 meters per second towards right, and then there is a body B which is moving towards left with a velocity of 5 meters per second. What do you think will be the velocity of A as seen by B? Do you see, by definition velocity of A with respect to B will be velocity of A minus velocity of B, and this is a vector subtraction. Velocity of AC is 10 I cap, 10 in the positive x direction, minus velocity of vector B or velocity of body B is 5 meter per second towards left. So, I can write it as minus 5 I cap, right. See what are we getting here? 10 plus 5 I cap, 15 I cap. So, the velocity of A with respect to ground, with respect to the road on which A is moving, is 10 meters per second, whereas when B observes A, B sees the velocity of A to be 15 meters per second greater than the velocity of A. Why is that happening? Because B itself is moving in the opposite direction. This explains to us why we feel those cars or those vehicles which are moving in the opposite direction to us, they seem to move quite fast in comparison to the vehicles that are moving in the same direction in which we move on the road while we are traveling. This is why it happens, because the relative velocity that we look bodies with when we are traveling on the road and we observe vehicles around us, we observe them with respect to us, considering ourselves at rest. So, with respect to us, then those bodies which are moving in the same direction, they seem to be moving slowly, whereas those bodies which are moving in the opposite direction, their velocity gets increased. Okay. So, when we talk about this aspect that there is an observer which is observing, and when the observer observes, he or she or it considers itself at rest, the space in which from where the observer observes, that space is called a frame of reference. So, there is an important aspect that comes in here in the chapter, in the topic relative motion, which is the frame of reference. Let us understand that as well. Frame of reference is essentially the space attached with the observer. So, when we say attached, it does not mean that there is something which is attached with the observer, nothing like that. The space in which the observer is. For example, if you are simply standing on the roadside and observing a vehicle moving, the space in which you are standing, which is the roadside, becomes your space or your frame of reference. Okay. If you're traveling in a car, you're sitting in a car which is moving on the road, and from that car if you're observing things around you, then that car becomes your frame of reference. It is with respect to the space of that car that you're observing bodies around you, right? That becomes your frame of reference, and when you're studying everything else around you, you consider your own frame of reference at rest. This is the important aspect of relative motion. So this is just a special name that we give to the space associated with the observer, which is considered at rest while observations are being made, the frame of reference. Okay, so understand that frame of reference is not it's not something, some alien concept or something. It's just a small term that we attach with the observer just to have a physical space associated with it, and through which we can work. Okay, so essentially, generally what we do is we generally represent the frame of reference with a three-dimensional space. The x, y and the z axis together, they form a three-dimensional space. We can call this space which is attached with the observer, that is observing the bodies, as its frame of reference. Okay, so nothing very different about what we have already observed here. Okay, now when we study this topic relative motion in class 11 physics, there are two major situations that we deal with. First situation is called the Rain-Man problem, and the other one is called the riverboat problem, which we shall take after this. So what we try to do here is, in the first problem, which is the Rain-Man problem, there is a rain which is falling down or maybe sometimes at an angle if there is a wind blowing along. Rain is falling and there is a person who's moving in this rain. So the situation is, this person is holding an umbrella and he wants to find out the exact direction in which he should hold his umbrella, the angle that the umbrella should make with the vertical direction, so that the rains fall exactly along the direction of the umbrella and he is saved from the rain, from getting wet as much as possible. Okay. Now why is this problem arising is because understand that if the rain is falling down like this, this is the velocity of the rain falling downwards. Okay. Had the man been stationary here, simply standing in the rain, not a problem, because if he is simply standing, he will see as if the rain is coming from the top, from his top, and he will simply hold his umbrella like this, right, and will be saved from the rain completely. But the situation now is that the man is moving in this rain. He is moving like this, velocity of man. This is the motion of the man itself. So then if we use relative motion, do we understand, as seen by the man, the velocity of the rain falling down will be different, right? Because when man observes, he will always consider himself at rest. He will not consider himself to be moving, though he is actually moving. So then we study the velocity of the rain as observed by the man, or as seen by the man, or relative to the man, which then by definition will be the velocity of the rain minus the velocity of the man, isn't it? So as soon as we come to this, now we understand that from relative motion, the speed as well as the direction in which the rain falls down will change as seen by the man, because of the state in which the man himself is. The way he is moving, that will now determine how the rain falls according to him, right? And to find out that, we need to use this basic definition. We need to get the figure if possible, and from there we can get our answer. So if we look at the situation here carefully, the velocity of rain is downward, whereas the man is moving towards right. By definition then, velocity of rain with respect to the man is velocity of rain minus velocity of man, which once again we can write as velocity of rain plus, added to that, negative of the velocity of the man. Now in the same figure, if I want to show that, velocity of the rain is downward, vertically down, whereas negative velocity of the man we can draw like this. Just opposite to the velocity of the man will be negative of the velocity of the man. This is the velocity vector minus Vm. And now we add velocity of the rain with the velocity negative of velocity of man, and the resultant will come out like this. Using the triangular law of vector addition, this is the direction in which the man will see the rain falling down with respect to him. So if according to the man, if the rain is falling down like this in this direction, he shouldn't be holding the umbrella vertically then, no, isn't it? He should be holding the umbrella like this in the direction in which the rain is falling with respect to him, right? So this is what we try to find out here. In fact, if you see here carefully, if we consider the angle phi that the vector VRM, velocity of rain with respect to man, makes with the vertical, we can easily find it out. We can say tan phi from this right angle triangle that we are getting over here. We can say that tan phi is equal to the opposite, which in this case is this negative vector Vm. Understand that negative vector Vm will have the same magnitude as Vm. Velocity of man will have the same magnitude as negative of velocity of the man, right? Only the direction changes. So I can simply write the length of this particular opposite for this triangle as Vm itself divided by the base. The base length is this, which is nothing but the magnitude of the speed of the rain, the velocity of the rain, Vr. So if we know the speed with which the man is moving and if we know the speed with which the rain is falling down, using this relation, then we can find out the angle that the vector Vrm will make with the vertical, which is nothing but the angle at which the man should be holding his umbrella to save himself from the rain as much as possible, right? We can also find out with what speed does the man see the rain falling with respect to him now. That is the magnitude of this vector Vrm here. See that the magnitude of Vrm we can obtain using the Pythagoras theorem once again from this right angle triangle. Can we say Vrm will be square root of Vr squared plus Vm squared? Isn't it? So from here we can find out both the things, the velocity of the rain with respect to man, the magnitude of that, as well as the direction of that, and then we can find out the direction in which the umbrella should be held by the man. So this is case 1 of the rain man problem. Case 1 is when the rain falls vertically down, right? The rain was simply falling down, right? Vr was simply downwards. What if there is a wind blowing during, when it is raining there, and the rain itself makes a certain angle with the vertical? Let us discuss that case also. So the case 2 here is when the rain falls at an angle. So the scenario looks like this now. This is the vertical direction, okay, and this time the rain is falling like this at an angle. Let us say this angle that the rain's direction makes with the vertical is theta, and the rain is falling with a speed Vr. So this is the velocity vector Vr, right? And now the man is moving in this rain in this particular direction, let's say horizontally with a velocity Vm, which will have a magnitude, and the direction as we have seen here, shown here, is towards right. Now the situation once again is, what is the velocity of the rain as seen by the man? How does the man sees the rain to be falling down, right? Once again, if we go back to the basic definition, Vrm should be Vr minus Vm, the vector difference throughout. So which will be velocity of rain, and added to that negative of velocity of the man. Now what will be the negative of the velocity of the man here? If velocity of the man is towards right, negative velocity of the man will be towards left, somewhat like this, minus Vm, right? And now when we try to get the resultant, the vector sum of Vr with minus Vm by using the triangular law, this is the resultant that we will get, this vector Vrm. See that depending upon the magnitude of Vm, this vector Vrm can change its inclination also. For now, the way we have taken it, this is how it is coming out. And let's say the angle phi that Vrm makes with the vertical now is this, right? So rain was already making an angle here, and due to the man's motion, now the angle that the rain makes with the vertical has changed, right? So once again, using the geometry of this figure, You can use the whole geometry. You know that this is a vertical, so these angles are 90 degrees. You know the magnitude of VR, you know the magnitude of VM. You can use the geometry of the figure to find out whatever you want. You can find out the length of this hypotenuse here. You can find out the angle phi. Right? It's just a matter of working with the geometry now. One more case that you can have here in the same case when the rain is falling at an angle could be, let's say that when the rain is falling in this direction, okay, when the rain is falling in this direction as we have already shown, VR, but the man this time is moving in this particular direction, opposite to it, like this. This is VM now. What will happen? In this case, understand that when we draw minus VM, it will come like this, minus VM. And then when we try to add VR with minus VM, the vector will come out like this, isn't it? Which is much inclined a vector in comparison to the first one. So initially the rain was inclined at an angle theta with the vertical, but as seen by the man, then the inclination, angle of inclination further increases. Why is that happening? Because the man is moving in the same direction from where the rain is coming. So he will see the rain falling at a greater angle. Whereas in the first case, the rain was falling in this direction, whereas the man was moving opposite to it. So that the angle of inclination of the rain falling with respect to the man as seen by the man, that decreased. Okay. So this is how situations will change. You always have to make sure that you are using the correct definition of relative motion, and then you are using the mathematical aspects to it correctly. You are considering the figure correctly. You are taking down values from the figure correctly. You are not making any mistakes here. For example, just to tell you a few values here, in the first figure that we have drawn over here, see that if we know this angle theta already, the angle with which the rain is falling, then we can find out this particular length, the opposite to this angle theta, which for this length being VR, the velocity of the rain, magnitude of that, this particular length will be VR sine theta. See that for yourself. Using trigonometry, you can easily prove that this length is VR sine theta. And then if we want to find out this particular angle phi that the rain's velocity with respect to the man makes with the vertical, you will be requiring this particular length over here, this small length over here, which you can then find out by using this total length, which is negative of vector Vm will have the same magnitude as Vm. So this total length is Vm, and you subtract from that this Vr, so that this particular small length that I am talking about will be Vm minus Vr sine theta. Because Vm, Vr and theta, all the three are known to you, that means this expression is known to you, and this will give you this particular length. And then you can also find out this opposite, this dotted line, the vertical that we have drawn over here, which is nothing but, okay, just to show you this, which one I am talking about, it is this green line, the vertical line that I have drawn just now. So this line will have a magnitude of VR cos theta. So see for yourself carefully, right? So if you know this perpendicular length and this base length, can we write from here tan phi? Phi is the angle that we are looking for, the angle that the rain's velocity with respect to the man makes with the vertical. Tan phi here will be the opposite by the base by definition, which is Vm minus Vr sine theta divided by Vr cos theta. So everything on the right hand side is known to you. Vm, Vr and theta, all the three are known to you. See that you can easily find out the value of tan phi, and hence phi. From here you can actually get to know what is the angle that the rain's velocity with respect to the man makes with the vertical, right? So this is the situation related to the rain falling at an angle because of some wind blowing. Okay, and this is how we deal with it. Understand that in relative motion, the vector diagrams help you a lot. They give you a lot of insight into the situation, and sometimes through the diagrams itself you can solve the questions. In the next video, we shall be taking up a few examples based upon the rain man problem, where we shall discuss various situations possible in this. For now, This is the Rainman problem, the first set of problem that we study in relative motion. Now we come to the second set of problem that we study in relative motion, which we call as the river boat problem, a very important topic in relative motion. The river boat problem, which can also be worked upon in the swimmer river problem. If there is a swimmer which wants to swim in a river, it will have the same situation as that of a boat that wants to move in a river. So the same two situations are similar. And also, if there is a case where there is an aeroplane which is trying to move in air where there is wind blowing, so aeroplane moving in wind, that's also a similar problem. So all these situations can be handled using this one single topic. If you understand this well, you will be able to handle all those topics very well. So let us look at this. What is this situation, the river boat problem? The situation is like this. We have a river flowing in a certain direction. This is the river, let's say, which is flowing in towards right with a velocity VR, the velocity of the river. Let's say we know the width of the river, it is W. Okay. And let's say there is a point A on one side of the river, the one shore of the river, the point A where a boat stands. This boat wants to cross this river. The boat wants to cross this river and it wants to go to the point which is right opposite to the point A on the other shore, the point B. The boat at A wants to reach the point B. But understand that in order to reach at point B, it will be difficult because there is river flowing in the rightward direction, right? So when the boat tries to move in this direction, the river will try to take it along with it. So what happens is the boat will move in a direction which will be like this, isn't it? In fact, there are certain terms that we study over here. You should understand them very well here. What is the nature of those terms? There is one term that we call as the boat's velocity with respect to the river, VBR. This is velocity of boat with respect to the river. As soon as we say with respect to the river, what do we understand from here? With respect to the river means relative to the river. That means velocity of boat when the river is considered at rest, when river is at rest. Now river cannot actually be at rest, but this basically means that when someone is trying to move, let's say in river which is not moving, in that case how will the boat move? Let us assume for a while that the river is not flowing. It's like a lake, not a river but a lake with water being still. In that case, do you understand that the boat will move in whatever direction you try to move it, in whatever direction you steer it, it will move in that direction, right? So can we say if for a while the river is considered at rest, then the velocity of the boat will be in that particular direction where you steer the boat, where you row the boat, isn't it? So let's say you row the boat, you want to move towards B, so you row your boat towards B. This is the velocity of boat with respect to the river from A to B. But this is the direction in which your boat will move if the river is still, isn't it? But now if the river is also flowing, can we say that river's flow will also take the boat along with itself? So what will happen is, if you want to find out the actual direction in which the boat moves, we just need to get the definition of VBR. VBR mathematically we know is velocity of boat minus velocity of river. This is by definition VBR. VB minus VR, this is what we understand from the basic definition of relative velocity, right? Now what is this VB minus VR? From here, can we write VB, velocity of the boat, is equal to VBR plus VR. What I have done here is I have just taken this term on the left hand side. to get the velocity of the boat. Okay, so what is VBR? VBR is the velocity of the boat with respect to the river when the river is still, whereas VB is the velocity of the boat when the river is also flowing. So VBR is that velocity of the boat with which the boat will actually move as observed by someone who is standing on the riverside, on the shore. If there is a person standing on the riverside and is observing the boat, then VB will be the velocity of the boat as seen by this person. Or in other words, you can simply say that it's the velocity of the boat with respect to the ground, the actual velocity with respect to the riverside, right? So this particular difference you must all understand very carefully. One is VB, the velocity of the boat, the actual velocity of the boat, and the other is VBR, the velocity of the boat with respect to the river, which is the velocity of the boat when the river is still, which is the velocity of the boat when the river is not flowing, or the direction in which the boat will move if the river is still. That is the direction in which you are steering the boat, right? I'm just talking about this again and again so that it becomes absolutely clear in your mind. Now let us come to the next step. Do you see that when we write VB, the velocity of the boat is the VBR, the vector sum of VBR plus the velocity of the river VR. What does this mean diagrammatically? If we look at the diagram here, VBR is upward, whereas VR is towards right. The river is moving in this direction towards right. Now you try to add these two vectors and see what is the actual direction in which the boat will move. The vector sum of these two vectors will give you the sum over here, no? Can we say this is the direction in which the boat will actually move? The velocity of boat will be in this direction. It is coming from this particular relation. See for yourself, right? So when someone rows the boat in this direction, the boat will not actually move in this direction. It will actually move in this direction because the river will take it along. And when it moves in this direction, it will not reach the point B. It will move, it will reach a point which will be somewhere here. Let's call it the point C on the other shore, which is quite far off from the point B, isn't it? So the question now comes is that if really the boat wants to reach the point B, how should the boat be rowed? How should it be steered? In what direction should it be steered? So from there, we understand that if we want the boat to actually move in this direction, we should steer it in a direction which is like this somewhat, so that when we add the river's velocity to it, the actual velocity then of the boat comes in the direction AB. Though this will involve some sophisticated physics to be used by the boat's person, which may not be entirely true, right? So the general case that we take up when we study a riverboat problem is this. I'll draw the figure once again and we shall see what is the most common situation that we encounter in the riverboat problem looks like. It looks like this. This is the river flowing towards right. Let me take it over here. This is the river, let's say. This is the point A. The velocity of the river is like this towards right, VR. And as we have already seen, this is the direction across the river, right? So that we reach the point B, which is just opposite of the point A. And if we want to actually move along the direction AB, then the boat should be steered in a direction which would be somewhat like this. VBR, the velocity with which the boat should be rowed with respect to the river, should be like this, so that when you now try to add these two vectors using the parallelogram law, see all of you, if you add these two vectors using parallelogram law, your net velocity of the boat comes out in this direction, isn't it? This is one possibility, right? This is one possibility where your boat can move exactly along the direction AB. But as I told you, this requires a very sophisticated physics, right? The boatsman may not be that good a physicist. So what the boatsman will do is he will try to move in the direction which is like making a certain angle. Let us get another figure here. So considering this point as A and the exact opposite point here as the point B. Okay, fine. And the boatsman try to move his boat like this in this direction, VBR, velocity of the boat with respect to the river. And then when you try to add it with the velocity of the river, which is like this, when you try to add these two vectors using the parallelogram law, your vector sum may not come out exactly along the direction AB, it might come out in this direction. Velocity of the boat would generally come out in this direction, and this is the general case that we take. The most general case that we take is this one, where the boat's velocity with respect to river makes an angle theta like this with the direction AB, mind you. And then the final boat's velocity comes in this direction, for which the boat will still move off the point B. It will still reach the other shore at a different point C, but this distance now between B and C will not be that large as it was earlier. Okay. So, this is the most general case that we study in the riverboat problem, and all our special cases come from here itself. We can derive them from here. So, let us look at this and do the mathematics associated with the riverboat problem one by one. So, to study the mathematics of a riverboat problem, let us once again write a few things. The width of the river is this W. Let us consider the river to be flowing along the x-axis. So, this is the x-axis, this is the y-axis across the river. And now, we can write all the known quantities in terms of the vector form with the rectangular component form of vectors. For example, we can write our velocity of the river as VR I cap. Because we know that the river is flowing along the x-axis, we can just take the magnitude of velocity of the river as VR, and along with that write I cap, the unit vector. So, that gives us the velocity of the river in its component form. Now, we write the velocity of the boat with respect to the river in its component form. See that the boat with respect to the river is in this direction, and we try to take its component over here. One component is like this length, and the other component will be over here, this length. See that the first component, which is along the x-axis, is VBR sine theta, and it is pointing towards left because of the way VBR is, it is towards the left side of the origin. This we are considering as the origin, the point A. VBR along the x-axis, the component will be VBR sine theta into minus I cap. See that it is pointing along the leftward direction. So, minus I cap plus the upward component will be VBR cos theta into j cap. All this is coming from vectors. Once again, if you are not thorough with vectors, I would advise you go back and revise your vectors first. So, now coming back to the expression that we have written above, that the velocity of the boat, the actual velocity of the boat is the sum of its velocity with respect to the river and the velocity of the river. When we do that, what do we get for the velocity of the boat? The velocity of the boat, which is velocity of boat with respect to the river, plus the velocity of the river would be, see here carefully, these two when we try to add these two components both are along the x-axis, this along the negative x-axis, this along the positive x-axis. Can we write this as VR minus VBR sine theta I cap plus the other component is the j cap component VBR cos theta j cap. So, the velocity of the boat, let me write this once again because this is an important relation. Velocity of the boat is VR minus VBR sine theta I cap plus VBR cos theta j cap. Now, from this relation, we understand that this velocity vector for the boat's velocity VB that we have obtained here it has got two components, one along the I cap direction along the flow of the river, which if you look at the figure will be a component over here like this, and the other component VBR cos theta will be along the vertical, along the across the reverse flow, right, from A to B in that direction. Now, do we understand from these two terms that the I cap component of the boat's velocity will not help the boat in crossing the river. It will only create a displacement along the flow of the river. This is the velocity of the boat along the river flow, and this is not going to help the boat cross the river, isn't it? Do we understand that it is this component of velocity VBR cos theta which will help the boat cross the river, because this is the velocity component across the river, velocity perpendicular to the river flow, and it is this component of velocity which will help the boat cross the river, right? So, this one aspect is very important to understand, and now we can find out a few quantities from here. So, the first thing that we look for is the time taken to cross the river. Time taken to cross the river. To find out the time taken to cross the river, we will consider the motion of the boat along the y-axis. We have already seen in projectile motion that we can always split a two-dimensional motion along two mutually perpendicular directions, and we can study both those motions separately, independent of each other. So, right now we are only discussing the y-directional motion, that is across the river along this direction. Across the river, understand that t, the time will be the distance travelled divided by the speed with which it is travelled, right? So, across the river, if the river has to be crossed, the width of the river has to be crossed. That means the distance to be travelled will be W divided by the speed with which is travelled. Now, what is the speed of the boat across the river? It is this component, isn't it? So, VBR cos theta. This then gives you the time in which the boat will cross the river, an important relation that you can use directly into your questions that come from the riverboat problem. Okay. Now, there is one special case that we can discuss here, which will be for what value of theta will the time for crossing the river be the minimum. Okay. So, when t is minimum, when is t minimum? Do we understand from this relation that when the denominator takes maximum value, the overall expression will take its minimum value, the time will take its minimum value. So, can we say that t will be minimum when cos theta will be maximum, that is 1, which will happen for theta being 0 degrees, right? And this will give us the minimum value of t. T minimum will be simply W by VBR. Now, what is the situation? What is the situation when theta is 0 degrees? Theta is 0 degrees means, come back to the figure, theta is 0 degrees means that the velocity of the boat with respect to the river is along the direction AB. That means the boat is directly being steered in the direction AB, which actually is this figure that we drew in the first place, this figure. Do you see here theta is 0? Now, in this case, observe carefully that the actual boat's velocity is not along AB. Actually, the boat will move in this direction along AC. So, it will reach quite far off from the point B. But the case is that the time that the boat takes to move from A to C or to cross the river will be the minimum here. Can you just look at the figure and understand why the time will be minimum for the boat to cross the river? Understand that in this particular case, the general case that we have taken, this velocity of boat with respect to the river is trying to oppose the river's flow, right? Do you see that this direction of flow of boat with respect to the river is opposite to the river flow? So, some part of this VBR is lost in compensating for the river's flow. So, just to oppose the flow of the river, some part of the boat's velocity with respect to the river is lost, and only a part of it is used to cross the river. Whereas, in this case, where you simply row your boat along AB, all the boat's velocity with respect to the river is taking the boat across the river. It is helping the boat cross the river. So all the VBR is used just to cross the river, and hence the river is crossed with the minimum possible time. Okay. So just keep this particular case in mind. This is the case when we have least possible time taken by the boat to cross the river. The next thing that we study here is what we call as the horizontal drift. Horizontal drift suffered by the boat. Horizontal drift, we call it capital D. Now what is horizontal drift? Let us see from the figure. The boat wanted to cross the river and reach the point B, which was just opposite to the point A. But it actually reached the point C, which is a little ahead of the point B, isn't it? So this horizontal distance between B and C is called the horizontal drift suffered by the boat. If you look at the figure carefully, you would understand that the horizontal drift D is nothing but the horizontal displacement or the x directional displacement of the boat in the same time in which it crosses the river and reaches the point C, isn't it so? So how do we find out the horizontal drift? All we need to do is it is the drift covered by the boat along the river flow during the course of crossing the river, right? So in the above figure, it is D is equal to the length BC, right? In this figure, it is this length BC that we are calling as drift. And how do we find it? Drift is given by the velocity of the boat along the river. Understand that horizontal drift will happen because of horizontal component of velocity, which is this component, right, along the flow of the river. So it is VR minus VBR sine theta multiplied by the time that the boat takes to cross the river, right? That's how we have defined the horizontal drift. So we just substitute the values here. VR minus VBR sine theta times, what is the most general expression for T? It is this, W by VBR cos theta, right? So this expression then becomes your expression for horizontal drift suffered by the boat in the process of crossing the river. Now a special case that we can take in case of horizontal drift is the case where we want the horizontal drift to be 0. We do not want the boat to move away from the point B. We want the boat to reach exactly at the point B. Okay, let us see what happens for that. Do we see that if we want for capital D to be 0, if we look at this expression, if we want capital D to be 0, that will be 0 when this particular term in the numerator goes to 0, isn't it? So can we say this implies VR minus VBR sine theta? This should go to 0, right? And if this goes to 0, what does that imply? It implies VR is equal to VBR sine theta, or sine theta is equal to VR by VBR. So if we have the river's velocity with us, and if we know the boat's velocity with respect to the river, we can choose the angle theta in such a way so that this equation is valid. And if that is the case, then the boat will exactly move along the direction AB and will not have any horizontal drift. See that we have already drawn the figure for that. This is the figure. So this is the angle theta chosen here, such that sine theta is VR by VBR, and then the boat exactly moves along the direction AB and reaches the point B exactly without any horizontal drift, right? So this is one special case in horizontal drift. Now there is a condition when this drift can be 0. What is that condition? Do we understand that sine theta can take values that are either less than or equal to 1? This is a limit for sine theta, right? The maximum value that sine theta can have is 1. From the above relation, can we say that this implies that VR by VBR has to be less than or equal to 1 if we want drift to be 0? That means that VR should be less than or equal to VBR. The river's flow should be smaller than, the velocity with which the river is flowing should be less than the velocity with which the boat moves in the river. Now, this is an important condition. This may not be true always, isn't it? The river might be flowing with a higher speed and the boat might be a manual boat which is being rowed, let's say, by hands. And in that case, this will be rarely the case that the boat moves with a speed greater than that of the river, right? So, what do we understand from here is that only if this condition is true, we can have a zero drift. If in case VBR becomes greater than VBR less than, it becomes less than VR, or we can say VR becomes greater than VBR. The river is now flowing with a speed more than the velocity of the speed of the boat with respect to the river. In that case, we say that drift being zero is not a possibility. Zero drift is not possible. If zero drift is not possible, then what do? Then we try to minimize the value of t. For d to be minimum possible, then understand that we are only talking about this particular case right now where VR is greater than VBR, when we know that drift cannot be zero. Now we are trying to find out another condition as to when the drift will be minimum. So we want to find out the condition for drift to be minimum, to find out the angle theta for which that will happen. And now we come up to an important aspect of differentiation. We have already studied that we can find out the minimum or the maximum values of quantities, or we can minimize and maximize quantities by differentiating them with respect to the variable on which they depend, and then put that equal to 0. So, that implies here that if we want the drift to be minimum, we can find out the derivative of d, the drift, with respect to the variable on which it depends, which in this case is theta. It is theta that we can change. Now, the angle that the boat's velocity with respect to the river makes, and we want to put that equal to 0 to find out the minimum value of t, right. So, this is the exercise that we shall be doing now. So, for that we shall first take down the expression for d, we will make some modifications into that, and then we will differentiate it. Okay. So, I will just write that down. D, as we have calculated, was VR minus VBR sin theta, which was the boat's velocity along the flow of the river, into the time in which the boat crosses the river, which was W by VBR cos theta. Let us take this cos theta inside the bracket, so that we get VR by cos theta minus VBR into sin theta by cos theta. And now let us make one more small change here. Can we write 1 by cos theta as sec theta? So, this will become VR sec theta minus VBR sin theta by cos theta can be written as tan theta, W by VBR, and it is this form of this formula for d that we shall now differentiate. So, this implies d of capital D by d theta is equal to, we are differentiating this particular function. Do you see outside these are constants, so we will keep them as it is, and we will differentiate this function where VR and VBR are also constants. It is only theta which is the variable, right. So, VR remains as it is. The differentiation of sec theta will be sec theta tan theta, right, minus VBR, the differentiation of tan theta will be sec squared theta, and the constants remain as it is. And now we are going to keep, we can maybe simplify this a little bit before we put it equal to 0. We can take a sec common, so it becomes VR tan theta minus VBR sec theta. We have taken a sec theta common outside into W by VBR, and now when we put it equal to 0, so that see that these constants will go away and we will be left with this term becoming equal to 0. So, VR tan theta will minus VBR sec theta will be 0, or VR tan theta will be equal to VBR sec theta, which when we solve, because we know that tan theta can be written as sin theta by cos theta and sec theta can be written as 1 by cos theta, the cos theta will cancel out, VBR by cos theta cos theta goes away and we are left with sin theta is equal to VBR by VR as our final expression for the drift being minimum. This is the condition for drift to be minimum. See that this expression is similar to what we got above for zero drift. Sin theta is equal to VR by VBR, right? Just see what is the small difference between these two. This is sin theta is equal to VR by VBR, whereas here it is sin theta is equal to VBR by VR. So, it is just the reciprocal of the above expression. Once again recall that the first expression was for drift to be equal to 0. When the rivers was flowing slowly, VR was less than VBR, whereas this expression, this condition is for drift to be minimum when the river is flowing fast, VR is greater than VBR, right. So, these are two important expressions for finding out the drift being 0 or being minimum in the two cases, and that finishes our study of a riverboat problem, a very important problem. You can use it into, you can just change or interchange the boat with a swimmer to make it a swimmer river problem, and you can change the swimmer or the boat with the aeroplane and the river with the wind to make it an aeroplane wind problem. So, all such problems can be easily tackled using this particular theory. In the next video, we shall take up some questions which will make us more comfortable with the topic of relative motion, in particular the situations of rainman problem and the riverboat problem.